I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. Part of the reason why we're doing these part twos is so that you can get familiar with the GSS variables, how to pull information from it, so that when you come to work on your final project, it won't be like the first time you've seen this interface. And you might find variables, you're like, oh, okay, I can use this variable, I'm familiar with it, I understand how it works or what it's measuring. So the question for part two was looking at, does the proportion of white people whose highest degree is high school, is that larger than the proportion of black people? And also, is the proportion of white people for whom college is their highest degree, is that larger for white people or black people? The first thing you do is you need to go under frequencies and cross-tabulation programs, which is usually the main page that pulls up, but you put your two variables in here. So you have race and then degree. As you can see, there's different variables for education. So the EDUC is more the quantitative version of education variable, and degree is more the categorical. Then I go here and I click on unweighted and unclick weighted, and that just gives you whole numbers so you're not turning someone into a decimal point. And then you do run the table. Here's where it gets a little bit tricky for wanting to look at the question of the proportion of white people with a high school degree compared with the proportion of black people. So if we want to find what our sample proportion is, so this is our null hypothesis, alternative hypothesis, what's our test statistic going to be? Rachel, do you want to try?
Well, you want to test the proportion.
Uh-huh.
So, like p hat.
Uh-huh. So p hat, the sample proportion of what?
White people with high school degrees.
Uh-huh.
And then the proportion of black people with high school degrees.
And how would we write it out here? Would it be plus, minus, equals, greater than? What we ultimately are going to need is a value that we're going to test. So you're right, it is greater than, but in order then to have a value to test, so then we do black people with a high school degree equals. And so the test statistic is going to give us a value. What we're going to do with that value is see how unusual it would be to get a value of that magnitude if the null hypothesis was true. When we talk about test statistic, what we're wanting is a value to sort of be our reference point for when we do the test. So with this, how would we calculate the proportion of white people with a high school degree? What numbers would I plug in? I'll go with Chelsea. So we want to find p hat white people where high school is their highest.
23,000.
Uh-huh.
And 44,000. Okay,
and why those two numbers? Why wouldn't it be 23,000 and 28,000?
Because that's like out of the high school in general, both white and black.
Yeah, so this will be something that will be important that you could easily get tripped up on. And this number can be confusing. You can always go up here and find the key. And this one says the first number is your column percent. And so what that's saying is 83.8% of people with a high school degree are white. But what we want to know is the proportion of white people with a high school degree, which is a different measure. And so It's just thinking through what's the subpopulation that I'm measuring, and then what within that subpopulation. In a sense, our subpopulation is white people, and we want to know what proportion of white people have a high school degree. You would take the count of white people with a high school degree as 23,000, and then divide it by the total number of white people in the sample. That's an easy thing where you could pull the wrong proportion out and then be doing a test on something that's very different from what you're trying to test. Same with black people, you do the count of black people where high school is their highest degree, and then the total number of black people in the sample. And then you can do the same thing for the second question, which is looking at people with a college degree. You can just pull this information. What's nice about this is we have this category called other, but you can just completely ignore it. You don't need to include it in any of your equations because you're just looking at white and black people, and this is a random sample of all white people and a random sample of all black people. So you don't even have to worry about the other category. That's how you get p hat, white people with high school degree, and black people with high school degree, and then we would get an actual value here, and I think it's 0.01. So our test statistic is 0.01. That's the difference in proportion of white people with a high school degree minus the proportion of black people with a high school degree.
So did you do 23,388 over 44,765, and then just went like
Yes.
like that? Okay.
Yep. Did you get a different number?
I think I ran the table the wrong way.
Well, and you could do degree as your row, and then it does it that way.
Yeah.
But it's going to give the same values. In fact, technically this way is the better way to do it because it actually, the way that the values in the cells are arranged, the first number is going to be column percent, and so that tells you the proportion of white people with a high school degree.
Okay, that makes sense.
So then this is the test statistic, and this is the thing that is our reference point. That's our anchor. That's the one thing that we have, and everything kind of revolves around that test statistic. If we want to do the confidence interval for the difference in proportions, we'd use our equation for confidence interval using this as our test statistic, or if we want to do a hypothesis test. With the hypothesis test, what we're wanting to know is how extreme would this test statistic be if there was no difference in the proportion of white people with a high school degree versus black people with a high school degree. How unusual would it be to get a value of 0.01? And so you have this test statistic, which is unstandardized. So it's just 0.01. And you might think, oh gosh, that's hardly any difference. But you don't know because it's unstandardized. So we standardize it using this formula. And this is the formula for the z statistic for a difference in proportions. When we calculate this out, what we get here is a value, and this is not the right value, but let's say it's 2.3, and this isn't the right value, but let's say it is. Where this is valuable of doing the standardized test statistic, we know that the standardized test statistic has this type of distribution. And what the standardized process does is it puts it in a standardized form so you can map it onto this standard normal distribution. So if we have a z statistic of 2.3, that tells us how unusual it would be to get a value of 0.01 if the null hypothesis was true. So if the null hypothesis is true, the center is going to be 0. And our standardized test statistic has a value of 2.3. So it tells us where on the distribution when the null is true. It says that it's right about here. What would be our formal decision with this hypothesis test?
Is there a better way to do that? Like once you have the z-score, because I was just kind of, last night I was going off the z-score and it was like, okay, it's less than 2, so I wasn't rejecting it, and it's more than 2, so I was. Is that correct?
That's a good shorthand.
Is that the other way to do it? Pull up stack key?
Yeah, you pull up stat key, you pull up your normal distribution, and we say the parameters are correct. It's a mean of 0, standard deviation of 1, and so then we go down. It's going to be right tail, and we enter in the value 2.3, and we see that it has a p-value of 0.01. As you do this more and more, this z-value provides a lot of information. It isn't just a random number that you're getting, but and then you'll get a sense for, oh cool, it's above 2, that means it's significant. Or if it's less than 2, it means that it's going to have a p-value of greater than 0.05, so it's not going to be significant. Also with like correlations, correlations have to be between -1 and 1. And so even just by knowing the bounds of your statistic is helpful, because then if you get a value that's like a correlation of 46, you're like, oh, wait a minute. And then you might look and say, oh, wait, it's 0.46, but I forgot to divide by 100 or something like that. So I think that's really helpful if you begin to get a comprehension of what these things are actually measuring. It can help you to know, oh wait, I made a mistake. Or if I'm asking for proportions, make sure you provide proportions and not percentages. Because if you're using percentages, you might be adding and subtracting numbers of different magnitude, if that makes sense. So the last 2 days we've been doing inference for categorical variables, for single proportions and difference in proportions, looking at calculating confidence intervals and conducting hypothesis tests. Today we're doing inference for quantitative variables, the first part, and we're just looking at how you do confidence intervals and hypothesis tests for a single mean. Fortunately, it's the same formulas throughout, but the values and the way you arrive at the values changes slightly when working with means. The X% confidence interval is your sample statistic plus or minus z star times the standard error, and where z star is a location on the standard normal distribution, and its value is determined by the confidence level that is selected. Even with this example here, this is our standard normal distribution. So everything comes back to the standard normal distribution, and so if we want to know, say let's do it on the stack here, a confidence level of 99%, confidence interval of 99%, how would we calculate that? How would we set that up here? If we wanted to know what z star is for a 99% confidence interval.
Can you go to two-tail?
Okay, two-tail, and then what?
Click the middle.
Mm-hmm.
Push 0.99.
Perfect. So then what's the z star? The value on the z distribution, that the upper bound of the 99% confidence interval.
Minus 2.575.
So the upper bound would be positive, both of them. Yeah, and those numbers will be the same. It's just easier to pick the upper bound because it's a positive number. So that's how we find z star. And then the same, we have hypothesis testing. And so z statistic equals the test statistic minus the null value over the standard error. And then the p-value is the area under the tails of the standard normal distribution beyond z. And so again, we have our standard normal distribution. When we do the hypothesis test, we're going to get a z statistic, and in this case it was 2.3. And so if we want to know the p-value, we want to know the proportion of values that are as extreme as 2.3. And so that's where we went on to StatKey and plugged in a cut point of 2.3, and it said the p-value was 0.01. Fortunately, on the back end of all of these, you're doing the same process. You're going to get a z-value, which is the standardized test statistic, and that's going to let you know how extreme your value is, and you can compare it to the null hypothesis. The central limit theorem, just like it applied to proportions, it applies also to sample means. And so this is a distribution of population values. Let's say this is income. And what type of shape does this distribution have? How would you describe the shape? Brittany?
Right skewed.
Okay, right skewed. So these are particular values, and if we did a random sample of this population of 100 people, what would the distribution of sample values look like? If we took a random sample from this population of, let's say, 100 people, and we were looking at income, what would be the distribution of sample incomes? Well, it's either going to be left skewed, right skewed, or bell-shaped and symmetric. And you say bell-shaped, what does the front row say? Bell-shaped. Well, okay, think about it though.
Or right skewed.
So when we do a sample, and if it's a random sample, yeah, it should match, because we're picking a sample that's representative of the population. And so with the sample values, the distribution is going to look just like the population. because it's pointing out a smaller version of the population. Say these are income levels, and this is 20,000, 40,000, 60,000, 80,000, 100,000. We're going to have the same values in our sample. If you need to convince yourself, I think it was 2 lectures ago, where there's that computer applet where it took the sample and it pulled down 20 samples from the population, and then the next thing it dropped down and gave the mean value of that sample. So the sample values, the sample distribution is going to look the same. So this is one sample. If we do the mean of this sample, the mean value of the sample is going to be roughly 3.5 is the sample mean. So this is the same process of we have a population, we take a sample of income values, and then we get a sample mean, which is 35, which we're going to call this 35,000. So this is our sample mean. Now, if we want to have a point estimate of the population mean, this is our best estimate from our sample, and it's the sample mean. If we took another sample from this population and calculated the mean is going to be slightly different than 35,000. It might be 35,100 or something. The sample statistic is going to vary from sample to sample. And so the sample statistics is going to have another type of distribution. What's going to be the shape of the distribution of sample statistics? We pull a sample out, we get all these values, and then we calculate the mean, and we get this sample mean, which is 35,000. If we do multiple samples and calculate multiple sample means, what's going to be the distribution of sample mean values? It can either be left skewed, right skewed, or bell shaped. Brittany.
That will be bell-shaped.
Okay, and why?
Because it'll always be around that mean. It'll be centered around the mean.
Uh-huh. If we were truly just doing 1,000 samples from this population, what is this sampling distribution going to be centered around? It'd be the population mean, so mu. The reason why this is important is no matter what the distribution of your population values are, the distribution of your sample statistic will be bell-shaped and symmetrical, or ultimately it'll be a normal distribution. And so because the values are normally distributed, it gives us the ability to do all the stuff we do with the standard normal distribution. So if we look at this particular distribution of values, even with a sample size of 10, we see that the distribution of sample values is similar to the population values. But then if you look at a distribution of sample means, like if you ran this 1,000 times, you would see that the sampling distribution is going to be symmetric and bell-shaped, which is the normal distribution. And then as we up the sample size, we see that it conforms to it even more. When we're looking at sample statistics, the distribution of those sample statistics will have a normal distribution. In a formal way, this is what it looks like. So this is X bar, our sample statistic. It's going to be a normal distribution, and it's going to be, the mean is going to be centered around the population mean, and then the standard deviation of the distribution is going to be sigma over the square root of n. It says smaller sample sizes may be sufficient for symmetric distributions, but 30 may not be sufficient for very skewed distributions or distributions with high outliers. So if your population distribution is skewed, you need to have at least a sample size of 30 for this to work. If you have less than that, then the properties of the normal distribution might not work. But everything that we'll be working with, for the most part, will have a sample size greater than 30. What we're interested in calculating is the standard deviation of this distribution. So calculating the standard error of a sample mean, the standard error for a sample mean can be calculated by sigma over the square root of n. And so sigma is the standard deviation of the population parameter. The standard deviation of the sample values is s. So if we use this, we have mean is x bar, and then s is the standard deviation of the sample values. And then the standard deviation of the population values is sigma. So that's just basically saying what is the general spread of the population values. And then the standard deviation of the sample mean is going to be sigma over the square root of n. And that's the sampling distribution of sample means. It's important to differentiate in your mind when we talk about the standard deviation of the sample distribution and the standard error of the sample statistic. So this last one here, the standard deviation of the sample mean is sigma over the square root of n. That's giving you the standard error of your sample statistic. It's letting you know how much this sample statistic varies, how much error is contained within that sample statistic, because what we know is that if we take multiple samples, this is going to vary a little bit. And so that's what standard error tells us. It's a standardized measure of the error that's in this variable. One property of it is that as your sample size goes up, the error in this variable is going to go down. It's just like, remember when we talked about height, and I said if my sample size was just 6 people, and I calculated a sample mean height, there'd be a lot of variation if I then took another 6 people and another 6 people. The sample means would vary a lot. But if I did like 500 people, the sample means that I would get wouldn't vary much at all. And that would mean that the standard error would be lower. And that's true with that equation, that as n goes up, standard error goes down. Brittany?
So that's finding the standard error of the sampling distribution, so the bell sheet.
Yes.
That's what this is.
Just like the sample proportions right here, we don't know the standard deviation of the population values, which is what sigma is. However, because our sample is a random sample of the population, the standard deviation of the sample values provides a good estimate of the standard deviation of the population parameter. So it's the same thing. In order to calculate standard error, we want to know what sigma is, which is the standard deviation of the population parameter, but we don't know that, and so our best estimate of it is the standard deviation of our sample distribution. So this sample distribution reflects the population, and so we can take the standard deviation of our sample distribution as an estimate of what sigma is in order to calculate the standard error. Standard error approximately equals s over square root of n. Almost the exact same slide from a few days ago. We want a standardized test statistic. The standardized test statistic is the number of standard errors. A test statistic is from the null value. Again, it's 2.3 in this example was our standardized test statistic, and it tells you how many standard errors it is from the null value. So this one was 2.3 standard errors from the null value. So it's similar to the z-score, just like z-score is the number of standard deviations, and observation sample value is from the sample statistic. The z-statistic is the number of standard errors from the null value. So we looked at z-distribution. This is a new term, and I still haven't figured out exactly why we need to use this, but I mean, I'll explain why we need to use it, but it doesn't vary much from what we've already looked at, but it does have slightly different properties. This is what we're doing with the z-statistic. We have the test statistic minus the null over the standard error. And so the value for standard error is sigma over the square root of n, and our best estimate of sigma is the standard deviation of the sample values. And so this is the standardized test statistic that we arrive at. But there's a problem in that if we replace sigma with s, it changes the distribution of the z-statistic from a normal distribution to a t-distribution. Because when we make that replacement, the distribution of values is going to shift slightly, and it's no longer going to be strictly a normal distribution, but it's going to change to be a t-distribution. The t-distribution is very similar to the standard normal distribution, except it has slightly fatter tails to reflect added uncertainty. And so here's what we've been seeing a lot is the normal distribution. And the t-distribution looks almost the same, but it's slightly different and has slightly different properties. So like the one example is that at 2 standard deviations away from the center, the tails are going to contain a little bit more information, 7.4%, whereas the tails 2 standard deviations from the mean contain only 5%, like this 95% confidence interval. It's just more spread out with the t-distribution. The t-distribution is the distribution of your test statistic. Like if you take multiple samples, what would be the distribution of your test statistic? When we're working with sample means, we're working with what's called a t-statistic. T-statistic is test statistic minus the null value divided by the standard deviation of the sample values divided by the square root of n. I'll say it isn't a major change. In the previous examples where we've been looking at the standard normal distribution, when we're working with sample means, we're going to look at t-distribution to see where our value fits relative to other values. Technically, the t-distribution is a family of sampling distributions because every sample size produces a slightly different t-distribution. There's a term called degrees of freedom, which is important in sort of knowing what your t-distribution looks like. The t-distribution is characterized by its degrees of freedom. So as the degrees of freedom change, the shape and the properties of the t-distribution change slightly as well. And degrees of freedom are calculated based on sample size, and the larger the sample size, the higher the degrees of freedom, and the closer the t-distribution is to the standard normal distribution. The t-distribution is already fairly similar to the normal distribution, and if you have a sufficiently large sample size, then it's going to look almost identical to the standard normal distribution. The black is the standard normal distribution, and then the red is when you have 5 degrees of freedom, and so you see it's just slightly different. And then when you hit 15 degrees of freedom, it becomes more similar. And then once you hit a certain number of degrees of freedom, it's going to look identical to the standard normal distribution. And why this is important is if you're working with something that's a really small sample size and you need to find the standardized test statistic for a sample mean, you need to use the t-distribution, because when you find the test statistic's place on the distribution, it's going to have different properties than the standard normal distribution. So the t-statistic is the standardized test statistic used with sample means, whereas the z-statistic was the standardized test statistic used for sample proportions. Just know when you're working with sample means, you're working with the t-distribution. In the same way, the t-statistic is a measure of location for a test statistic on the t-distribution. Just like in the example earlier, we had a value for z. When we do these equations, we're going to have a value for t. It's going to be a number like 1.6. And you're going to say, okay, where does 1.6 fit on the t-distribution? And in the same way, the t-statistic is the number of standard errors a test statistic is from the null value based on the t-distribution. This restates what the z-statistic is, and so t-statistic is for sample means, z-statistic is for sample proportions. Just sort of mapping all these out so that you can have it clear in your mind. And then z-score is when we're looking at sample values and we want to know where does a particular value fit in relation to the sample statistic. So then the relationship between t-statistics and p-values, once you've calculated the t-statistic for a test statistic, you can obtain its p-value, again using StatKey, and it's an identical process, but just looking at a different distribution. This is the standard normal that we've been looking at, and then you'll see here is the t-distribution. Also take note that there's the chi-squared distribution and the f distribution, so that's a foreshadowing. But here's the t-distribution, so you click on that. So if you have a standardized t-statistic and you want to know what the p-value is, you go to the t-distribution and you need to plug in the degrees of freedom. So we'll say degrees of freedom is 1499. You'll be given what the degrees of freedom are. So this is the t-distribution with a degrees of freedom of 1499. In the same way, you want to find out what the p-value is. You figure out, is it a right tail or left tail or two tail, and you go in and plug in whatever your value was for t. Say our value was 1.6, and so then it would give you the p-value, which is 0.055. It's the same process, but you're referencing a different distribution with sample means. Yeah.
Degrees of freedom, something that we'll have to calculate, or will that be?
Yeah, but it's super easy.
Okay.
It's very, very easy, fortunately. It's probably the easiest formula. And then we're going to do our two things that we do with inference, which is confidence intervals and hypothesis tests. So calculating confidence intervals for single means, if n is large or the sample data is normally distributed, a confidence interval can be calculated by the same formula that we've been working with, except for instead of using z star, we're using t star. because the sample statistics are distributed in the form of a t-distribution versus a standard normal distribution. So then our sample statistic is x bar, and we have t star, and then our standard error is s over the square root of n. And the degrees of freedom for a single mean is just n minus 1. And there's a complex reason for why that is, but it's just simple if you just know the degrees of freedom is whatever your sample size is minus 1. So we know how to calculate x bar, we know how to calculate the standard deviation for the sample values, and we know what the sample size is, and we just looked at how to find t star. If we want to know what t star is for a 90% confidence interval, how would we do that? So t star is a measure of location on the t distribution. Rachel?
Can you use stat key?
So you go to stat key, and so we hit t, and then it wants to know what are the degrees of freedom. We'll say, well, actually, Rachel, give me a hypothetical sample size.
Okay, 1,000.
Okay, so then what would the degrees of freedom be? Okay, just so you know, versus like, wait, why was it always 999 or whatever? So degrees of freedom is just whatever your sample size is minus 1. Okay, so we're wanting to know what t star is for a 90% confidence interval. Then what's the next step, Rachel?
Two-tail.
Okay, perfect. Two-tail. And then our t star.
Would be 1.646.
Yep, exactly. Fortunately, I know like 3 days ago when you first tried to do the homework with this stuff, it was like, what are we doing? So by virtue of repetition and some of this stuff overlaps a lot, it'll help to make it a little bit more clear. So that's how you find t star. And again, t star is a location on the t distribution with n minus 1 degrees of freedom, and its value is determined by the confidence level that is selected. The second thing that we do with inference is hypothesis testing. And for single means, we want the distribution of the sample mean assuming the null hypothesis is true. What's the distribution of our sample statistic when the null hypothesis is true? So again, this is all familiar stuff, but just applied specifically to single means. So our standardized test statistic is the t statistic, and it's the test statistic minus the null value over the standard error. When we were working with proportions, it was the z statistic. When we're working with means, it's the t statistic. If we substitute in the actual symbols, we have x bar, which is our test statistic, minus mu naught, which is the null value if the null hypothesis was true. And then s is the standard deviation of the sample values, and square root of n is the sample size. The t statistic is going to give you a value. It's going to be somewhere between like -10 and +10, because it's going to be somewhere along that t distribution. So it's not going to be a huge number. It's going to be a standardized version of your test statistic. And so then the p-value is the area in the tails beyond t in a t distribution with an n minus 1 degrees of freedom. The t distribution changes shape slightly as the degrees of freedom changes or as the sample size changes, so that's why they have that disclaimer with a n minus 1 degrees of freedom. That's why it's important just to know what the sample size is, so that when you're asking the computer to provide a t distribution, you'll know what the degrees of freedom are. Okay, so an example. We're going to do an example that covers both confidence interval and hypothesis testing. So Chips Ahoy, if you read the package, says 1,000 chips, chocolate chips, in every bag. And we're wondering, is this claim true?
I just got the Chips Ahoy thing.
Oh, you did?
Yeah, no, I just never got why it was called Chips Ahoy until right
Oh.
now. I didn't even play on words.
So are there truly 1,000 chips in every bag? So our population would be every single Chips Ahoy bag in the world, and we could go and count every single bag and count all the chips. That's unrealistic, and so what we can do is do a sample. To test this claim, a group of randomly collected 42 bags of Chips Ahoy cookies from all over the country and hand counted the number of chips in each bag. This is true. And they found that the sample mean was 1,261.6 chips. The mean number of chips per bag was 1,261.6, and the standard deviation was 117.6 chips. So these are the sample distribution. This is sort of our starting point. This was our sample, It's a random sample of the whole population of Chips Ahoy bags, and these are the sample statistics that we arrive at. So we can use this information to do both confidence interval and hypothesis testing. So really, a lot of times, all you'll get is the sample size, which is 42, the sample mean, and the standard deviation. With just that information, we can do all these other tests and inferences to the population. Does this data provide sufficient evidence to conclude that there are at least 1,000 chips in every bag? So before we even do confidence interval or hypothesis test, does this data alone provide sufficient evidence to conclude that there is at least 1,000 chips in every bag? Well, why can't we just say, hey, we looked at 42 bags and the mean was 1,261. That seems like, you know, every bag has at least 1,000 chips. Why can't we just sort of stop there? Well, we need evidence. Why wouldn't you be convinced, Rachel?
Well, the sample size is too small.
It's small, but even remember when we do a sample of the US population, which is 300 million, 330 million people, and we had a sample size of just 1,500 with the Obama approval rating.
Yeah.
So actually, there's calculations that you can do, and it would actually say that 42 is sufficient. So this is our one sample statistic, and we need to know how much will that sample statistic vary? Like how much error is in that sample statistic? Because if we took another 42 bags of Chips Ahoy and counted the chips, what would our sample mean be? It would be slightly different, but how different would it be? And so that's why we need to do confidence interval. And it does matter on the sample size, like the number of bags. But even if I said, okay, well, 100 bags, would that convince you? You'd be like, I don't know, maybe, or 1,000, you know, so we need a quantitative way to say how much would this sample statistic vary from sample to sample. If there's a large variation and it dips below 1,000, we're like, this isn't sufficient evidence. In fact, we can't reject the null hypothesis because it looks like there's not enough evidence to reject it. So there's two ways to look at this. It depends if we are sufficiently confident that the interval estimate, which is the point estimate plus or minus the confidence interval, is greater than 1,000, or it depends on how likely it would be to get a sample mean as extreme as 12,061 by random chance if there was not 1,000 chips in every bag. Confidence interval and hypothesis testing address the same question but from different directions. The confidence interval says, let's look at our point estimate of 1261.6 and let's see what the confidence interval of that is. And in this case, if the confidence interval includes values that are less than 1,000, then we know there's not sufficient evidence to say every bag has at least 1,000. Or we could do hypothesis testing and say, let's pretend every bag has less than 1,000, or that there's bags that have less than 1,000. What are the chances that we would get a sample statistic as large as 1261 if our null hypothesis was true? So confidence interval and hypothesis tests are interrelated. They just approach it from a different direction. I'll explain at the end why one is preferred method over another. So to validate this claim that Chips Ahoy is making 1,000 chips in every bag, we can either calculate the confidence interval of the point estimate or conduct a hypothesis test. Just to be sure, we'll do both. So with confidence interval for single means, I'm going to just sort of walk you through the process. This gives you your sample statistics. So the sample size is 42, degrees of freedom is 41, sample mean and standard deviation of the sample values. So the first is to check the conditions. Earlier we had said if you have a sample size that's greater than 30, you can use the t-distribution equations, the equations based off of the t-distribution. We want to find t-star for a 95% confidence interval, and that's what we just did on StatKey. You go in, do a two-tail, and you click on 0.95, and that'll give you the t-star, which is 2.02. So that's for a 95% confidence interval. And then you calculate the confidence interval, and the equation that we had shown earlier is right here, and it gives us a confidence interval of 1,224 to 1,298. That gives the confidence interval for our point estimate of 1261. The way we interpret these results is we are 95% confident that the average number of chips per bag of Chips Ahoy cookies is between 1224.9 and 1298.3 chips. And so basically, we're 95% confident that every bag has at least 1,000 chips in it. And then the way you'd walk through a hypothesis test, again, same sample statistics. You start by stating the hypotheses. This comes up sometimes. Not always is the null hypothesis 0. So in this case, we're saying that the null hypothesis is 1,000. The alternative that we're testing is to see if the sample mean is greater than 1,000, because we want to see if it's true that the mean number of chips per bag is greater than 1,000. So we check the conditions. Sample size is greater than 30, so we can use the formulas for the t-distribution. And then we calculate the test statistic. T equals 14.4. Remember how I said like the t will range between -10 and 10? Well, this one's 14.4, and it's like, wow, that's really big. Why do you think that's so big? What is it that we're testing? It's because the difference between our sample mean and our null value is so large. If your sample is a really big value and there is a really big effect, then your t-statistic is going to be really large. Because the effect is so large, the chances of getting this type of value when the null hypothesis is true is like almost just impossible. It's like the chances of it are so small. So we have a t-value of 14.4, and Chris, do you want to help me figure out what the p-value is for 14.4?
You still go to theoretical distribution,
Uh-huh,
right?
yep.
T. It's 41.
Yep, 41. And then is it a right tail or left tail?
Right.
Uh-huh. So right tail. Our t-value that we want to see where it fits on the distribution, what do you think the p-value is going to be? Okay, something incredibly small. So yeah, I mean, and what that's just saying is, if there were only 1,000 chips per bag or less, the chances of getting a sample mean of 1,200 chips per bag is super small. And so it's basically saying we have very strong evidence that there's more than 1,000 chips per bag. Because if it wasn't, the chances of us getting a sample size of 1,200 is just super small. So we have a p-value of effectively 0, and then to interpret the results is this provides extremely strong evidence that the average number of chips per bag of Chips Ahoy is significantly greater than 1,000. Again, to validate this claim, we can either do confidence interval or a hypothesis test. Both methods validate the claim, but the hypothesis test lets you know the strength of the evidence supporting the claim. So the confidence interval just says that it doesn't contain the value. It either does or doesn't. Whereas the hypothesis test lets you know the strength of the evidence. And so with this particular hypothesis test, we see that the strength of the evidence is super strong against the null hypothesis. So if the null hypothesis is true, there's an extremely low probability that we would observe a sample mean as large as 1,261 by random chance. So with the confidence interval, we just kind of know it's either in or out. With hypothesis test, we're like, wow, this is super strong evidence, or this is sufficient evidence, but not super strong. Brittany?
For the confidence interval, though, couldn't you go back and change, like if you did a 99%?
Yeah, so that's a way you can tweak the confidence interval. You could say, well, we want to be 99% confident, but still you wouldn't know. You'd have to redo it each time to see, well, I'm 99.9% confident. And really, with this one, you can be 99.99999. You know, it's like, so just doing the test once, the hypothesis test once, lets you know how confident you can be. These are just some characteristics of t-distribution, and that's all. With the final project, I use a term in the write-up called ordered categorical variables. To keep our project simple for you guys, I want you to use either quantitative variables or ordered categorical. And an ordered categorical variable is a categorical variable where the categories are in order. It's a progression. So like with degree, that's an ordered categorical because the lowest value is less than high school and then it progresses up to graduate degree. Whereas race would not be an ordered categorical variable. because is black greater than or less than Hispanic or greater than or less than white? Like it isn't ordered. So when you're looking at variables, look for quantitative or ordered categorical. And the last one that you could use is binary categorical. So if you wanted to just look at white and black, or if you wanted to look at Christian and Jewish or something like that, you can do that. That could be something that'd be good to talk to your tutors about, of like, hey, I need to pick variables. Begin to think through what variables are easy to work with. It makes the analysis much more complicated if you try and do other types of categorical variables.